Okay, continuing our discussion with matrices. The first new matrix we're going to look at today is what we call the identity matrix. Okay. The identity matrix has it's a square matrix. It's always n by n. Okay. And what it boils down to is all the entries in the matrix are 0 except for the main diagonal running from top left down to bottom right. Okay. So if we have a 2 by 2 identity matrix, it would look like 1, 0, 0, 1. That would be the 2 by 2. We had a 3 by 3. It would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So those are both the identity matrices for 2 by 2 and 3 by 3. And what it boils down to is that they're called the identity matrix because when we multiply these matrices by any other 2 by 2 or 3 by 3, okay, we get the same thing back. So if I were to take any 2 by 2 matrix, multiply it by this matrix, okay, I would get the same thing back. And hence the identity matrix. Okay. Now, the equivalent to this, and we kind of talked about this a little bit on our last part, is that very similar to numbers, okay, these matrices have similar properties. Okay, we know that we have an identity in the integers, which is 1, because if I multiply a number by 1, I get the same thing back. So this matrix is kind of like 1. If I multiply by it, I get the same thing back. Now, the next thing that we talked about when we had an identity in terms of multiplication is a multiplicative inverse. Okay, if I take the number 2 and I want to multiply it by something and get 1, okay, I know that multiplicative inverse is going to be the reciprocal of 2, which is 1/2. Okay, and so we say that 2 and 1/2 are multiplicative inverses of each other because when we multiply them, we get the identity. Fair enough? So similarly, when we have a matrix, whether it's a 2 by 2 or a 3 by 3 or otherwise, okay, some matrices have multiplicative inverses. In other words, we can find a matrix that we could multiply by it and get back to the identity matrix. Okay? So that's what we're going to look at next. Okay. So the idea of having an n by n matrix, keep in mind that we're only talking about square matrices, either 2 by 2, 3 by 3, 4 by 4, and so on. Okay. So we say if there's a matrix B, such that if we multiply A times B, or notice B times A, okay, that we get the identity matrix. That means that A and B are inverses of each other, and when we write the inverse, we use the same notation as we did for sine and cosine and so on. Okay, we write A to the negative 1. Okay, that means A inverse. So A inverse and B would be the same. Okay, provided that when we multiply them either way, okay, we get the identity matrix. Okay. So next question we might ask then is how do we find such a matrix that would have that property? Okay. The answer for a 2 by 2 matrix is as follows. If I have entries A, B, C, and D, if I want to find the inverse, okay, then the answer is going to be 1 over AD minus BC times this new matrix DA. Notice the A and the D are switch spots, and the C and the B do not switch spots, but they become negative. Okay, so this is ultimately the formula for figuring out the inverse of a 2 by 2 matrix. And notice one stipulation here is that AD minus BC cannot equal 0, because you'll notice if it was 0, it would be on the bottom of 1, which is not okay. Okay. And this quantity that we have here, okay, is what we call the determinant of the matrix. Okay, that cannot be 0. If the determinant is 0, then there's not going to be a matrix. Okay. So with that said, do all matrices have inverses? No. Okay, because if I find one that has a determinant of 0, okay, then there is no inverse. Okay. All right. So let's go ahead and try one. We're going to go to this one. So this is our matrix A. We want to determine whether it has an inverse, and if so, we want to find the inverse matrix. So remember what we need out in front is 1 over AD minus BC, oops, AD that is, minus BC. Okay. So let's figure out what that is first. So AD minus BC for us, which is going to be our determinant. Okay. So this is A, B, C, and D in the general notation. So it would be 15 minus and then BC is 8, 1 times 8, and so therefore our determinant would be 7. So in the first question, determine whether it has an inverse, we could say yes, because the determinant does not equal 0. So we would say yes, it does have an inverse. Okay. And then the inverse, remember in general, is going to be dA, and then negative B, negative C. Okay. So let's see how that's going to look then in practice. We're going to have 1 over 7 out in front. Okay, if I switch the D and the A, I'm going to have 3 here, 5 here. And if I negate the B and the C, I'm going to have negative 1 there, and I'm going to have a negative 8 there. Okay. And then to actually get the inverse, remember this is like having a scalar multiple out in front. We learned on Friday that if we have a scalar multiple out in front, we could just multiply the scalar multiple by each of the entries individually. So my final answer here then will be 3/7, negative 1/7, negative 8/7, and 5/7. Fair enough? Okay. So our claim is that this matrix is A inverse. Okay. So if it is A inverse, then what should happen when I multiply these two together? I should get the identity. Okay. So let's find out if that's true or not. So we can prove that we're right by doing the matrix multiplication. So I'm going to multiply 3/7, negative 1/7, negative 8/7, 5/7. I'm going to multiply these two matrices together and show that they are in fact inverses, because the result here, if I did it right, had better be 1, 0, 0, 1. Okay. So let's do first row times first column to get our first entry. Okay. So if I do 5 times 3/7, that's 15/7. Okay. And if I do 1 times negative 8/7, that's minus 8/7. And if I do 15/7 minus 8/7, that's 7/7. And what is 7/7? It's 1. Okay. So good start, right? That's what we wanted to have there. If I do first row, second column, 5 times negative 1/7 is negative 5/7. 1 times 5/7 is 5/7. And those two together are going to make 0, which is good. So far, so good. Second row, first column, we got 24/7 and negative 24/7, which gives me 0. Okay. And then finally, last row, last column, negative 8/7 and 15/7, which again is 7/7, which of course equals 1. Alright, so we do in fact get the identity. Now remember, that really is only halfway to the proof though, because if these two are inverses of each other, it shouldn't matter, okay, which way we multiply them. Okay. And that's the same property that we had with inverses of other situations in the past. Okay. Same thing with numbers. Like I said, with 2 and 1/2, it wouldn't matter which way I multiply them. I get 1 either way. I'm not going to take the time to multiply them the other way, but if you switch these two around and do the multiplication, okay, you would in fact get the same result. I do want to show you a couple things with the calculator here that you can use to check. We make our matrix. I'm going to make my matrix A a 2 by 2. Make it 5, 1, 8, and 3. So my matrix A is stored. And then if I want to find the determinant of the matrix, you do have an option for that. If you go to your matrix, and then you go under math, okay, you have that first command is DET. And under matrix again, if you type in matrix A, it'll find the determinant of it for you, which of course is pretty easy to do by hand with a 2 by 2 matrix. More difficult with a larger matrix, as we'll see in a minute. But we can figure out the determinant with calculator as well. Okay, the other thing that we can do is take the matrix and use our -1 power button right here on the left. And if we do that, it gives us the inverse of that matrix. Another nice feature is that it does give it to us in decimal form, but as long as it can be written in fraction form, you can hit math frac, and it'll take the matrix and put it in fraction form for you, which is convenient. Okay. And you notice that we did in fact have the right answer, right? We also could store that matrix, let's say in B, matrix B that is. So let's store that in B. Okay. And then we can also show that if we go matrix A times matrix B, we had better get the identity matrix, which we do. We could also show it the other way. If I go matrix B times matrix A, okay, I in fact get the identity matrix there as well. Fair enough? Okay. Questions so far on anything about the calculator? Alright, now, with anything larger than a 2 by 2 matrix, okay, there is a method for finding the inverse. Okay. What we're going to do though by hand is we're just going to be able to find the determinant of a 3 by 3, okay, and then after that, okay, everything's going to be a calculator problem if it's 3 by 3 or bigger. Okay. So I am going to show you how to do the determinant of a 3 by 3. Okay. And I'm going to do it with this problem right here. We're going to take a 2, negative 1, 1, 1, 0, 3, 1, 2, and negative 1. Okay. And we're going to go ahead and find the determinant of that. Okay, we're not going to actually find the inverse by hand. We're just going to find the determinant only by hand. Okay. Of course, we can use the calculator to find the determinant to check. But the procedure is as follows. When we have a 3 by 3 matrix, we're going to take the first 2 columns, okay, and we're going to rewrite them outside the matrix as such. Okay. All right. And then what we're going to do is we're going to start with the top left entry, the 1, 1 entry, if you will. Okay, and we're going to draw, and I usually draw a line through the diagonal. Okay. And what we're going to do with those numbers that I just drew a line through is we're going to multiply them together. So if I do 2 times 0 times negative 1, that's going to be 0, of course. And then the next one, I'm going to do the same thing with these 3. And if I do 1 times 2 times negative 1, I'm going to get 2. And then finally, I'm going to do these 3. And when I do those 3, I'm going to get 1 times negative 1 times 3. That's negative 3. Okay. And then what I'm going to do is I'm going to add those all together. Okay. So I'm going to take those 3 diagonals, multiply the entries, and we're going to add them all together when we get them all done. And so in this first one, we're going to have negative 1 as our result. Okay. And then what we're going to do is we're going to subtract the quantity that is 3 more diagonals, okay, going backwards from the top right. So in my diagram, I'm going to take these 3 next. So I got 1, negative 1, negative 1. Multiplied together, that all would be 1. And then if I do these 3, I'm going to get 2 times 2 times 3, which is going to be 12. And then finally, if I go 1, 0, 1, I'm going to get 0. And again, I'm going to add those entries all together. And so in this parentheses, I'm going to have a 13. And so the determinant of this particular matrix is negative 14. So what that tells us is that that matrix does have an inverse, because the determinant's not 0. Same rules for the 2 by 2. So we can tell that it does have an inverse. Okay, but again, like I said, by hand, all we're going to do is just calculate the determinant. Okay, after that, we're going to use the calculator to actually find the inverse matrix. Fair enough? Okay, but I do want you to be able to do that skill by hand, so that's something that you're going to want to practice when you are doing your homework. Make sure you can do that. So again, we rewrite the 2 first columns. Okay, we cross out, if you will, okay, the first 3 diagonals going to the left, multiply the entries together and add them up and get a total. And then coming backwards, we start with this one, this one, and this one. Multiply the entries, okay, add them up to get a total, and then ultimately we subtract those 2 to get our final answer for the determinant. All right. Questions so far? All right. To finish up, Elizabeth. No, the actual, remember the actual determinant in the previous example was AD minus BC. Okay. So with the inverse, it was just out front. It was 1 over the determinant. Okay. And again, we don't need to. All we care about is the determinant itself. Okay. So it's obviously calculated a little differently than AD minus BC because there's more entries. Okay, but that is the determinant. Okay, so we would label that as D, if you will. Okay. So out in front of the 2 by 2, we had 1 over the determinant times the new matrix. Okay. Good question. All right, just to finish up here, just to talk about some properties of matrices. Just summarize what we've learned so far. The commutative property, we do have that for addition. Okay, 2 matrices can be added in either way and get the same result. Multiplication, okay, does not hold in general. Okay, we cannot necessarily multiply A times B and B times A and get the same thing. Okay, matter of fact, depending on the size of the matrices, it's not even an option to multiply unless the inside dimensions are equal. Okay. The associative properties, both for addition and multiplication, are going to be true always. Okay. The identity property for addition, we do have a 0 matrix that we can add to any matrix and get the same thing back. Okay. We do have an identity matrix for multiplication that we can multiply either way, okay, and get the same thing back. Okay. And remember, in multiplication, that would only be for a square matrix. Okay. We do have an inverse property for addition. If we do the negation of a matrix and we add it to the original, we'd get the 0 matrix back. Okay. We do have multiplication identity inverses as long as the determinant does not equal 0. And notice the notation for the determinant they use here. Okay. They write it as an absolute value of A. Okay. That means the determinant of. As long as the determinant does not equal 0, then we do have a multiplicative inverse. Okay. And then the distributive property is also true for matrices. And so you'll notice that a lot of the properties that we have for regular numbers, okay, are also true for sets of matrices. Okay. All right, so for our work today, we're going to finish up the homework assignment for section 7.2. Okay.